Hi everyone. Today I'm going to talk about atomic force microscopy, AFM. AFM is a very high-resolution type of scanning probe microscopy, which is used to see and measure the surface of sample at nanometer scale. This is more than 1,000 times better than the optical diffraction limit. The AFM has been used in all fields of science, including chemistry, biology, physics, material science, nanotechnology, astronomy, and medicine. The first atomic force microscopy was invented in 1985 based on the principle of scanning tunneling microscope, STM. If you're not familiar with STM, you can watch this video. For this STM-based atomic force microscopy, it has an AFM tip, which directly touches the sample surface. When the tip is dragged across the surface, the AFM cantilever oscillates up and down. This deflection of cantilever can be monitored by tunneling current to STM tip. After several decades development, we now have this modern AFM. Instead of using the STM tip, the deflection of the cantilever is detected by the reflection of laser beam. So, how does it work? Well, we know that the Pell potential energy varies by the distance between two atoms. When they become closer, they will have attractive force between each other, such as van der Waals force. But if they become too close, repulsion force such as Pauling repulsion and ionic repulsion is applied. So, if the tip becomes close or too close to the sample surface, attractive or repulsion effect will occur. This will make the cantilever bend towards the direction or the opposite direction of the surface. And the reflection of the laser beam will deviate from the center point. Finally, this deviation can be transformed into our desired electronic signal by a photodiode. Based on this principle, three major imaging modes have been developed. The first one is the contact mode. In this mode, the tip always directly contacts the sample. The distance between the tip and the sample surface is very small, so the repulsion force is applied. Since the tip can feel or touch the surface all the time, this imaging mode often gives a very high resolution. However, the tip and the surface can be damaged, especially after taking numerous scans with contact AFM mode. We also have a non-contact AFM mode. In this mode, the tip of the cantilever does not contact the sample surface. The cantilever is instead oscillated above the surface. The van der Waals force or any other long-range force that extends above the surface act as the attractive force, and they decrease the resonance frequency of the cantilever. Because it is non-contact, the sample surface is not damaged. This makes it preferable for measuring soft samples such as biological samples and organic thin film. However, in ambient conditions, most samples develop a liquid layer, and in the non-contact mode, an AFM will oscillate above the adsorbed fluid layer to image both the liquid and surface, lowering its resolution. In conclusion, the contact or non-contact mode both have their own disadvantage. Keeping the tip close enough for better resolution, while at the same time preventing the sample and tip from damage is a challenge. So, people develop tapping mode to bypass this problem. Nowadays, tapping mode is the most frequently used AFM mode. In this mode, the cantilever is driven to oscillate up and down near its resonance frequency, and both attractive and repulsion force can be applied. Since the tip can actually touch the surface, the resolution of tapping mode is higher than non-contact mode. Besides, the duration of this direct contact between tip and surface is much shorter, so tapping mode imaging will not damage the sample surface. It is gentle enough even for the visualization of soft surface, such as supported lipid bilayers and adsorbed single polymer molecules.